Hi everyone. Happy Wednesday. Welcome to the Chem Help ASAP live stream that we do every Wednesday. I hope that y'all are doing well. So this week, as you can tell from my title, we are going to be doing stoichiometry. Now we are going to be adding sig figs into all of these calculations as well, because I know that's one place where students sometimes have a hard time taking their rules and their practice from their sig fig and applying it to all of these chemistry calculations. So we will also be talking about how to get the correct number of sig figs when you're done with your calculations. Okay, so it looks like OG Benchmarks is already on the job, and we will go ahead and start our first question. And of course, as always, if you've got a question, post it in the chat. I will be checking the chat periodically, and I will do my best to answer any questions that you have. Okay, so our first problem here, we're going to start with a really simple stoichiometry. So I want to make sure we lay the foundation before we get into some more complex problems. So this first stoichiometry problem is just a mole to mole problem. Now, of course, whenever we do stoichiometry, we are at some point going to have to go through moles because we need to use our mole ratio. And I'll talk a little bit about that and how we find that mole ratio as well. So anytime you're doing any kind of stoichiometry problem, the first thing that you really want to think about is moles, and either how do I get to moles, which is usually the first question, how do I get to moles? And then after moles, then what do I do? So let's go ahead and jump into this first problem, and we'll just deal with moles. So we've got a couple of questions here. Let's just read the first one here. So if 2.50 moles of water react completely, how many moles of hydrogen gas is formed? Now, if you just ask this question without any context, you wouldn't know what was going on, but the critical piece of information is we are given a chemical reaction here. So let's first take our chemical reaction and let's balance it, and then let's start talking about the stoichiometry component to this. All right, so for balancing this equation, I just tend to move left to right, although you don't have to. So I have 1 calcium and 1 calcium. I've got 2 hydrogens, but I have 1 oxygen and I've got 2 hydrogens here. Remember, that is a multiplier. So I am going to, let me get up my pen here. I'm going to need to put a 2 here. So that takes care of my oxygen, but of course that changes my hydrogen. So I need to go back and reevaluate hydrogen. This is going to give me 4 hydrogen, and I have 2 here plus 2 here. So I have 4 hydrogen. So I am all set. So this was a pretty easy one to balance. Okay, so let's go back to our actual question. Again, I'm just doing the first one. So it gave me information about water, and then it asked me information about hydrogen gas. So the first thing that I like to do is identify this as a stoichiometry problem. And the way I know that is because it has given me information about one molecule, asked me information about a different molecule, and I connect these two molecules based on my balanced chemical equation. So that is an easy way and a reliable way to identify a stoichiometry question. And then once you know you've got a stoichiometry question, if you haven't already found your chemical equation of balance, that you want to do that. But also you want to be thinking, okay, I'm going to need to move through moles at some point in this problem because I'm going to need my mole ratio. So the great thing is we are already starting in moles, so there's no need to do a lot of conversion before we jump into that mole ratio. But what I'm going to do first is I'm just going to write down what I was given. So I was given 2.50 moles of water. Okay, so to convert from the molecule water to the molecule hydrogen gas, this is where I need my mole ratio. And my mole ratio comes from my balanced chemical equation. It is simply the coefficient in front of each of my molecules. So first I'm going to look at water here, and I have a 2 in front. This is why we balance before we jump into the stoichiometry. So oftentimes those coefficients in front of our molecules are called stoichiometric coefficients, and they give us our mole ratio. So what I'm going to do is I'm going to use my ratio of 2, which is water, and I'm going to hydrogen, which means I'm going over here. Now, one thing I want to point out, there is no number written in front of the hydrogen molecule, which means that number is 1. So if the number is 1, we don't write anything down, but if it's something different, we will put a number in front. So my stoichiometric ratio is 2 to 1. Now I want to set this problem up such that my moles of water divide and I'm left with moles of hydrogen gas in my numerator. So I'm putting in my units first. I want my moles of water to divide out, and I want to go to moles of hydrogen because that's what was asked. Now I'm going to put my numbers in, again, my stoichiometric coefficients. There is a 2 in front of my water right here, and of course in front of my hydrogen we assume there is a 1. Now what this does is it sets my units up to cancel like so. So once you hit stoichiometry, you probably have already done dimensional analysis. And stoichiometry really is very, very similar to dimensional analysis. If you let your units lead you, then it can very often lead you through the stoichiometry problem itself. Especially with these kind of stoichiometry problems, we are not dealing with limiting reagents. So my moles of water cancel. I'm left with moles of hydrogen, which is exactly where I want to go. It's what the question asked for. So I'm going to take 2.5 and divide it by 2. So this gives me 1.25 moles of hydrogen. Okay, let's do sig figs, just like I said we would do. So we're doing multiplication division here. So we're going to find our number with our fewest number of sig figs, and that's going to tell us how many sig figs our answer should have. So I'm going to switch to a different color here. So our 2.50 has 3 sig figs, and our mole ratio, you might be initially tempted to say, well, that just has 1 sig fig, but this is an exact number, so therefore it has an infinite number of sig figs. So your mole ratio will never limit your sig figs in any way. So that means my answer needs to have 3 sig figs, which actually. I already have, so I don't need to round this any further. So my final answer is 1.25 moles of hydrogen. Okay, let's move on to the next part of this question. So if 0.025 moles of calcium hydroxide were formed, how many moles of calcium reacted? So again, I am given information about calcium hydroxide. I am asked about moles of calcium. I have switched molecules. I need to connect those with a balanced chemical equation, which we already have, so that's pretty easy. So I'm going to do stoichiometry, which means I need my mole ratio. And again, with this problem, we're starting in moles and we're ending in moles, which makes it really simple. So I'm just going to write down what I was given. I was given 0.025 moles of calcium hydroxide. And now I need to move into moles of calcium. So again, I'm going to find my mole ratio, which is just my numbers written in front of my different molecules. So my number in front of my calcium hydroxide, again, is 1 because there's nothing there. And in front of my calcium is also 1. So this is a 1-to-1 ratio. These are the ones that we love the most because they're the easiest. But let me set it up, show how the units cancel. So I want my moles of calcium hydroxide to cancel. So I'm going to put those in the denominator. I am trying to determine moles of calcium, so that goes in the numerator. And now I'm just putting my stoichiometric ratio in, my mole ratio, and it's just a 1-to-1. So there's a 1 and a 1 here, which makes this math fantastic. So now this is moles of calcium. Again, let's do our sig figs, although you probably already know where this is going. So my 0.025 moles of calcium hydroxide has 2 sig figs. Remember, these leading zeros are not significant. Again, my mole ratio has an infinite number, so my final answer should have 2 sig figs, which it does. Easy peasy, right? Okay, the great thing about doing moles is generally the math is not too difficult. Okay, so let's go with our final just mole to mole stoichiometry. So I have 3 times 10 to the 5th moles of water react completely how many moles of calcium? So again, I'm going from water to calcium. That means stoichiometry. That means mole ratio. So let's set this up. So I have 3.00 times 10 to the 5th moles of water. It's a lot of moles of water. Okay, and let's get my mole ratio for that. So in front of my water, I have a 2, and in front of my calcium, I have a 1. So I want my moles of water to cancel, so that's going to go in the denominator. I'm trying to predict moles of calcium, so that goes in the numerator, and now I'm just putting my numbers in. So again, in front of the water is 2, and in front of the calcium is a 1. So now all I need to do is take my 3 times 10 to the 5th and divide by 2. And that is 1.50 times 10 to the 5th moles of calcium. Okay, so the moles of water have canceled here. I am left with moles of calcium. Let's talk about sig figs. Okay, so this 3.00 times 10 to the 5th, remember, scientific notation, every digit is significant. So these 2 zeros are significant, so we have 3 sig figs. My mole ratio has an infinite number, which means my answer should have 3 sig figs. So this is correct because I included my 0 right there. That also has 3 sig figs. Before we leave this problem, I do want to kind of point out a bit of the nature of this problem. So in our first part, we went from water to hydrogen. So we went from a reactant to a product. You can do that with stoichiometry. And our second part, we started with a product and then we predicted a reactant. So you can also go product to reactant. And in our third part, we started with a reactant and we actually predicted our other reactant. So stoichiometry, we usually think of it as reactants to predict products, but you can go any which way in the balanced chemical equation. So yes, reactants to products, products to reactants, reactants to reactants, and also products to products. As long as you've got a balanced chemical equation that bring these molecules together, you can use stoichiometry to move however you want through these problems. Okay, let's make sure there are no questions. I don't see any questions yet, which is good. Hopefully you find the mole-to-mole stoichiometry really easy, but it really lays the foundation for moving into the more complex problems. Okay, so in our next stoichiometry problem, we are now going to be dealing with grams. But again, we want to make sure that we keep moles in mind because we are going to have to use that mole ratio at some point in the problem. It's just really a matter of when and how we use it. Okay, so let's read through the problem. How many grams of hydrogen and oxygen gas will form when 13.67 grams of water undergoes decomposition? And then if 0.0105 grams of oxygen gas was formed, how many grams of hydrogen was produced? Again, so we've got kind of a multi-part question. We'll deal with the first part of the question first and the second part of the question later. But we need a balanced chemical equation, and we definitely do not have a balanced chemical equation here. I've got 2 oxygen, so I'm definitely going to need a 2 in front of here, which changes my hydrogen. I'm going to also need a 2 in front of here. So, all right, now we've got, just double check, yes, we've got a balanced chemical equation. Now, even though all of these problems are stoichiometry, let's identify this as a stoichiometry problem. So in this first part, we were asked how many grams of hydrogen and oxygen are formed when 13.67 grams of water. So we are given information about one molecule, in this case water, and we are asked information about another molecule or molecules because we're asked about hydrogen and oxygen. So again, this is why we need a balanced chemical equation to move between these molecules. So to start this problem, let's just write down what we were given. We were given the 13.67 grams of water. Now, stoichiometry is all about the mole ratio, which means we need to be in moles. And right now, we are not in moles, we are in grams. So the next question we have to answer is, how do I go from grams to moles? Well, you need to use your molar mass. So making sure that my grams of water cancel and I convert to moles of water. In molar masses, it's always 1 mole of whatever molecule you're talking about. And of course, the number of grams changes depending on the molar mass. So for water, this is 18.01528. I'm going to squeeze that in a little bit. So when doing molar masses, it is easy to start getting a little lazy and start rounding your molar masses off. Now, sometimes this is not a problem. Maybe you just need to do a really quick stoichiometric calculation and the number of sig figs doesn't matter. But in all of these problems, because we are also focused on sig figs, I want to make sure that any constant that I bring in, i.e. molar mass, has got a good number of sig figs more than whatever I'm starting with. So because I'm starting with 4 sig figs, I want to make sure that my molar mass has more than 4. It has to have at least 4, but I like it to have more than 4 sig figs as we move forward in this calculation. Okay. So back to the calculation itself, we are not finished yet. So right now we have our grams of water have canceled. That's fantastic. We now have moles of water. Well, now that we're in moles, we can use our mole ratio, we can use our stoichiometric coefficients, and we can convert from water to another molecule. Well, the first part of this problem asked about hydrogen and oxygen. So let's just do hydrogen first because it was written first. So I want to make sure my moles of water cancel. I am first predicting moles of hydrogen, so that goes in the numerator. Oops, that looks a little funky there. Now let's get my mole ratio from my balanced chemical equation. There is a 2 in front of the water, and there is a 2 in front of the hydrogen. Okay, so what this does, it means my moles of water have canceled. I now have calculated, even though I haven't put it in my calculator yet, moles of hydrogen gas. Is that what the problem asked me? So if you go back to the problem, you see that it wants grams. So we are not finished yet. We need 1 more conversion factor, and this time we're going to convert from moles of hydrogen to grams of hydrogen. So putting in units first, I want my moles of hydrogen to cancel, and I want to be left with grams of hydrogen. So of course that is always 1 when we're talking about a molar mass. And for your molar mass of hydrogen with plenty of sig figs, so I'm not just going to put 2. And again, I had to kind of squish that a little bit. Now my moles of hydrogen have canceled, and you can see the only unit I have left is grams of hydrogen, which is exactly what the problem asked for, which means I can now calculate this quantity. So if I do this, and I'm just going to write down a lot of digits here, your calculator will give you, oh, so many digits. And now let's talk about sig figs. Okay, so for the number that the problem gave me, my starting number has 4 sig figs. My molar mass of water has 1, 2, 3, 4, 5, 6 sig figs. My mole ratio, of course, has an infinite number, and my molar mass of hydrogen has 1, 2, 3, 4, 5, also 6 sig figs. So again, when you're doing this and you're checking sig figs, you do want to make sure that the molar masses you have calculated are not limiting you in terms of your answer, in terms of your number of sig figs. And that is true in this case. My molar masses have plenty of sig figs. I need 4 sig figs in my answer, which means I'm going to round at that 9 right there. Whoops. So my final answer is 1.530 grams of hydrogen. Now it is important that you include that 0 because remember you need 4 sig figs. So if you just dropped the 0 and you report it as 1.53, that only has 3 sig figs. So that 0 is important because it is a significant digit. Okay, so that was grams of hydrogen gas. Let's do the same thing, but this time we're going to do it for oxygen gas. So starting with what we were given the 13.67 grams of water. Now, the nice thing about doing this is you're going to see that we're going to repeat a lot of the same things. Again, grams of water, we need to first convert to moles of water. So I am just going to write the same conversion factors down that I did for the first calculation. And again, my grams of water have canceled. I'm left with moles of water. Now I need to make sure that I'm going to use my mole ratio between water and oxygen gas. So I still have my 2 moles of water. That is not going to change. And now I'm going to oxygen, which has a 1 in front of it. So that goes to oxygen. And now I've converted out of moles of water and I'm in moles of oxygen. But of course, I need one last step. I need the molar mass of oxygen, and so that I can calculate grams of oxygen. So I want my moles of oxygen to cancel. Of course, that is always a 1 with molar mass. And just like before, I'm going to do too many sig figs. Well, you can't have too many sig figs, not in my opinion. Okay, I am going to do this. I'm starting to run out of space already, and we still have a whole nother part. Okay, so now my moles of oxygen have canceled. I am left with grams of oxygen, which is what my problem asked for. So now I'm going to put it in my calculator and run through this calculation. Again, my calculator is going to give me so many decimal places, and they are not all significant. So let's talk sig figs. Okay, so my starting number again has 4 sig figs. My molar mass of water, just like before, has 6. My mole ratio has an infinite number, and my molar mass of oxygen has 1, 2, 3, 4, 5, also 6 sig figs. So I'm limited by the number that the problem gave me, which is the way you want it to go. So I need 4 sig figs. I'm going to round right there. So my final answer is 12.14. Make that decimal a little bit bigger, grams of oxygen. Okay, I'm going to need an extra page here because I just can't fit everything there. So let's get an extra page. Perfect. Okay, but let's go back and let's make sure we know what we're doing. So For our last part of this problem, we are given 0.0105 grams of oxygen, and we are asked how many grams of hydrogen was produced. So this is a product to predict another product, which is fine. It's still stoichiometry because we're given information about one problem, and we're given information about one molecule, and we are asked information about a different molecule. So let's come over here, and I am just going to rewrite my balanced chemical equation. I am going to leave off states here just because I want to write it quickly. And let's also get my number I started with, 0.0, so I'm going to bring it over here, 0.0105, and that is grams of oxygen. Okay. And again, we're using this to predict the other product. We're using it to predict grams of hydrogen. Because we're doing stoichiometry, we've got to get to moles. So if we're starting with grams, we need a molar mass to get to moles. So I am going to use the molar mass of oxygen. So I want my grams of oxygen to cancel, and I am going to convert to moles of oxygen. So this is, of course, 1 moles, and my molar mass of oxygen is 31.9988. We have seen this before. Okay, so my grams of oxygen have now canceled out. I'm in moles of oxygen, which means I can use my mole ratio to convert from oxygen to hydrogen. So I want my moles of oxygen to cancel, and I am going to convert to moles of hydrogen gas. So there is a 1 in front of the oxygen here and a 2 in front of the hydrogen gas. And of course, we have one more conversion factor. Let's see, let's cancel out our moles of oxygen. So we need to convert from moles of hydrogen to grams of hydrogen. So I need a molar mass, making sure that my moles of hydrogen cancel, and I'm converting to grams of hydrogen. So for molar masses, of course, it's always 1 mole. And the grams is to, again, put a lot of significant figures in there. And that cancels out my moles of hydrogen. I'm left with grams of hydrogen, which is what my problem asked for. So putting this in my calculator and writing it down with too many decimal places, times 10 to the negative third grams of hydrogen gas. Let's count up sig figs. Okay, so starting here, I have 1, 2, 3 sig figs. Again, remember, whoops, that 3 did not come through, did it? Those leading zeros are not significant, but this is a captive zero. It is. Molar mass of oxygen, I have 6 sig figs. Mole ratio is infinite. And for hydrogen, 1, 2, 3, 4, 5, also 6 sig figs, which means my starting number, the number I was given, limits me, which is really what I want. So I need 3 sig figs, which means I'm rounding right there. So let's rewrite this with the correct number of significant figures. 10 to the negative third grams of hydrogen. Okay, let's see if there are any questions. No questions? All right, great. So that is a gram to gram stoichiometry problem. Let's go on to a next one. So I've mixed in a lot of different kinds of stoichiometry problems here. I'm actually not sure if I will get through all of them before we hit 8 o'clock, but I'll just get through as many as I can. Okay, so let's read this one. A 0.75 kilogram bar of aluminum is dropped into a 0.985 milliliters of hydrochloric acid. After the reaction is complete, what is the concentration of aluminum chloride? Okay, so we've got a couple things going on here. We weren't given grams, we were given kilograms, so that's a little bit of a twist. And this time we were asked about concentration as well. But let's first identify this as a stoichiometry problem. How do we know it's a stoichiometry problem? Except for the fact that the title of the live stream is stoichiometry. So I am given information about aluminum. I'm also given information about hydrochloric acid, but I am asked about concentration of aluminum chloride. So I'm given information about one molecule. I am asked information about another molecule. I'm going to have to tie these two together with a balanced chemical equation. Now, right now, I do have a chemical equation, but this is not looking very balanced to me. So let's balance this equation before we jump into the actual math here. Okay, So it's looking to me like I've got 3 chlorine atoms here and only 1 here. So let's put a 3 there. And that gives me 3 hydrogen and 2 here. Okay, so this is not totally working, right? I can't rectify 3 hydrogens on the reactant side and 2 hydrogens on the product side. So I need to do something else besides putting 3 halves in front of hydrogen. So if you're in a situation like this and you have that kind of odd ratio, the best thing to do is to multiply by 2. So instead of putting a 3 in front of my hydrochloric acid, I'm going to try a 6 and see if that works instead. Okay, so that means if I have 6 hydrogen here, I need to put a 3 in front of my hydrogen gas there, and that now my hydrogens are balanced. Now let's go back and look at chlorines again, because of course I unbalanced when I changed that to a 6, but let's see if we can fix that. So I just need a 2 in front of my aluminum chloride, which means I need a 2 over here. So very often as you're balancing these types of reactions, I know until balancing gets a little bit easier and you're a little more confident with it, you can get kind of stuck and say, oh no, I can't put that number here because it's going to unbalance another atom. Just go atom by atom. It's all right if it unbalances another one, or it's all right, like in this case, when I balanced my hydrogens, I actually undid the balancing that I started with when I started balancing my chlorine atoms. That's actually okay. It's totally fine because you can always go back later and rebalance that. So don't be afraid to, when you're balancing, to put a number in front of a molecule, even if you know, oh, that's going to unbalance something else. What you want to do is you want to go 1 atom by 1 atom. But again, multiplying through by 2 is a pretty common thing that you see when balancing more difficult equations. So if you're really, really stuck, just erase everything and start with a 2 instead of starting like here. I started with a 1 in front of the aluminum. Start with a 2 in front of the aluminum and balance from there. Okay, that was just my little balancing spiel. Let's get back to our stoichiometry. Okay, so again, we're given information about aluminum and we're asked about aluminum chloride, which means we've got to get to moles. Now, you might also be saying, but we were given information about hydrochloric acid. Okay, so we were given a volume of hydrochloric acid and we were given a mass of aluminum. So the volume of hydrochloric acid, without a concentration and without a density, we're going to not be able to get to moles there. But because we have a mass of aluminum, we can absolutely get to moles of aluminum. So aluminum is what we want to start with in this case. So I'm going to start with my 0.75 kilograms of aluminum. Okay, so I've got to get all the way to moles. This is not just a one-step process. This is a two-step process. Because the first thing I need to do is to convert from kilograms to grams. Now, again, as these get easier, instead of actually writing down 0.75 kilograms, you might already move that decimal in your head. That's totally fine. But for these exercises right here, I am going to explicitly write down each step. So in 1 kilogram of aluminum, there are 1,000 grams. Okay, so my kilograms of aluminum have canceled. Now I have converted into grams of aluminum. Because I'm in grams of aluminum, I can convert to moles using the molar mass. So of course, I want to make sure that my units cancel first. So I need to make sure grams of aluminum is in the denominator and moles of aluminum is in the numerator. That is going to be a 1, and this is 26.98153 grams of aluminum. Okay, so my grams of aluminum have canceled. I now have moles of aluminum. And of course, I needed to get to moles of aluminum because I am using a mole ratio. Okay, so let's just get our units in first. Moles of aluminum, and I'm trying to predict aluminum chloride. So I'm going to moles of aluminum chloride. All right, so let's see, was that a question? No. Okay. Let's get our stoichiometric coefficients. I have a 2 in front of the aluminum here, and I also have a 2 in front of the aluminum chloride. Okay, great. So my moles of aluminum have canceled. Now, when we talk about concentration, there are multiple ways to measure concentration. In the absence of any more information, this is going to be molarity. Because I know I can get to moles, I've actually just calculated moles, and I also need a volume, which is actually right here. Okay, so we're going to do molarity, which means I am not going to convert these moles of aluminum chloride into grams of aluminum chloride because I need moles to calculate molarity. So I'm going to end this first part of this calculation right here and actually get my moles of aluminum chloride. Again, I'm going to write down lots and lots of decimal places, 6, 7, 9. This is moles of aluminum chloride. Oh, squeeze that in just a little bit. Now, because I am not finished with this calculation, I am not actually going to round it. I'm just going to put a little line underneath where I need to round. So let's talk about sig figs. I started with 0.75 kilograms of aluminum. That has 2 sig figs. This conversion factor here, this is an exact conversion factor, so it has an infinite number. My molar mass of aluminum has 1, 2, 3, 4, 5, 6, 7 sig figs. And of course, my mole ratio has an infinite number. So I am limited to 2 sig figs, which means I want to round right here. Again, I am not going to actually round there yet because if I round too early, I will introduce rounding error into my final answer. So again, I just put a little line over where I need to round so that I remember when I go to the next step, hey, this is where you need to round for the correct number of sig figs. Okay, let's go to the next step, which is getting concentration. So molarity is moles of solute over liters of solution. We definitely have our moles. We've got our moles of aluminum chloride, which is great. Now we need our liters of solution. This is total liters in whatever you're doing. Now in this case, we're doing a reaction. So the only source of real volume that we have, because we can assume that the bar has reacted, and so we don't have to mess with that, is our 985 milliliters, and that came from the hydrochloric acid. But of course, this is in milliliters, and we need liters. So we need to do what I call a side calculation first, and we need to convert this milliliters into liters. So if I have 985 milliliters, to convert that into liters, just use the conversion factor of 1,000 milliliters in 1 liter. And all this does is this bumps the decimal place 3 spaces to the left. So I have 0.9850 liters of solution. Now I have all of my numbers that I can plug into my calculation for molarity. So I'm going to put in my moles. Again, I'm keeping all of these decimal places for now, but I'm also going to give myself my little line there to remember, and then my liters of solution. Okay, and then this is going to give me my concentration, which again, written with lots of decimal places, of aluminum chloride. Now let's get to our final rounding with the correct number of sig figs. Okay, so remembering that our aluminum chloride was rounded right here to the ones place, which means it has 2 sig figs. Now our volume has 1, 2, 3, 4 sig figs. And I just want to point out this is a common thing. So in this milliliters, of course, I had a 0 in the tenths place. When students convert this into liters, very often they will drop that 0, but that is a significant digit, and you want to make sure you carry it forward and you count it in your sig figs. So our volume actually has 4 sig figs, not 3. That's a really common mistake that I see, which means my answer needs to have 2 sig figs. So again, I am rounding to the ones place. So my final answer is 28 molar, and that is aluminum chloride. So that is a concentration problem. So that one had a couple of twists, and it wasn't just one long calculation. We actually did a couple of calculations. Okay, let's make sure there are no questions. All right, and let's move on to the next problem. Okay, it looks like we're dealing with some gases here. So let's just read through. If 7.12 times 10 to the third liters of sulfur dioxide react with an excess of oxygen at STP, how many grams of sulfur trioxide are formed? And then, if the same volume of sulfur dioxide reacts, but is now at 0.850 atmospheres and 15 degrees Celsius, how many grams of sulfur trioxide are formed? Okay, so in our last problem, our twist was concentration in kilograms. And in this problem, our twist is we are dealing with gases. Now, how do we know this is a stoichiometry problem? Okay, we are given information about sulfur dioxide, and we are asked information about sulfur trioxide. So again, we need a balanced chemical equation to relate these two to get our mole ratio. The great thing about this problem, I guess because they figured we're going to work hard with our gases, is they have already balanced it for us, which is fantastic. All right. So now let's talk about how we're going to get to moles. And we're just going to do the first part of this question, and then we'll get to the second part because we get to moles a different way. So the important thing to note here is, okay, so we have a volume of a gas, but we are at STP, which is standard temperature and pressure. This is 0 degrees Celsius and 1 bar, although sometimes people talk about it as 0 degrees Celsius and 1 atmosphere. It's close enough that we can call it the same thing. But that is STP, standard temperature and pressure. Now, the great thing about being at standard temperature and pressure is you can use what's called the molar volume of gases, which is about 22.4 liters per mole. Now, this is for ideal gases, but we are assuming in this case that all gases are ideal. So that is an easy way to convert from volume to moles for an ideal gas, but only at STP. And I really want to emphasize that because this is another very common problem that I see students doing when they have gases is they want to apply the molar volume to all gases at all pressures and temperatures, and you cannot do that. It is only at STP. Now, I know it's tempting because it's very easy, but you do have to be careful about that because you'll end up with the wrong answer, even though it's an easy way to get an answer. Okay, so let's start with what we're given. Let's start with our 7.12 times 10 to the third liters of sulfur dioxide. Again, because we're doing stoichiometry, we want to get to moles. So that is the ultimate goal, is to get to moles so we can use our mole ratio. So my molar volume is going to convert my liters of sulfur dioxide into moles of sulfur dioxide. Again, I want to set this up so that my liters of sulfur dioxide cancel and I'm left with moles. Well, in the molar volume, this is 1 mole and this is 22. And I'm going to give this a couple of extra sig figs here. Okay, so our liters of sulfur dioxide have canceled. Now we have moles of sulfur dioxide, which means we can jump straight to our mole ratio. Okay, so I know I want my moles of sulfur dioxide to cancel, and I'm going to go to sulfur trioxide. Eventually I'm going to get to grams, but I can't do grams yet. I first got to convert molecules with my mole ratio. Okay, let's get numbers in here. So there is a 2 in front of our sulfur dioxide, and there is also a 2 in front of our sulfur trioxide. So that's a 2-to-2 ratio. That's great because that simplifies to 1-to-1. And then let's see, we want grams. So hold on, let me cancel out these moles of sulfur dioxide. And at least this is an easier conversion. Well, it's not more difficult mathematically, but mentally, I think, because, of course, to convert from moles to grams, we just need the molar mass. So I want my moles of sulfur trioxide to cancel, and I'm going to convert to grams of sulfur trioxide. That is 1, and let's get a number with plenty of sig figs. 3, 2. And then my moles of sulfur trioxide have canceled, and I am ready to get an answer here. Okay, so plugging all this in, I'm going to write down what my calculator gives me and all of these crazy decimals. And that is grams of sulfur trioxide. Let's talk sig figs. All right, so here's the number I was given that has 3 sig figs. My molar volume here has 1, 2, 3, 4, 5 sig figs. Of course, my mole ratio is infinite, and my molar mass here is 1, 2, 3, 4, 5, 6 sig figs. Okay, so I am limited by what the problem gave me, which is again where I always like to be, if at all possible. And so I have 3 sig figs, which means I need to round to 3 sig figs right here. So this is 2.54 times 10 to the 4th grams of sulfur trioxide. Okay, great. Let's see if there are any questions. No questions. That's fantastic. Let's keep on going. We've got a second part of this one, and it's not going to be quite as easy because we're no longer at STP. Okay, so if the same volume of sulfur dioxide reacts, but is now at 0.85 atmospheres and 15 degrees Celsius, how many grams of sulfur trioxide are formed? Again, it's still stoichiometry because I am given information, granted a lot of information, about sulfur dioxide, but then I'm asked information about sulfur trioxide. So I'm still looking for that moles because I know I'm going to have to go to that mole ratio. All right, so let's think about all this information that we're given for sulfur dioxide because we've got to get to moles. So I have a volume because it's the same volume. I also have a pressure and I have a temperature. So hopefully you've got bells going off and you go, oh, it's ideal gas law. So remember ideal gas law, PV equals nRT. And this is how we're going to calculate moles for our sulfur dioxide because now it's no longer at STP. So let's plug in what we've got. We've got a pressure here, which is 0.850 atmospheres. We have the same volume that we had before, 7.12 times 10 to the 3rd liters. This is going to give us our number of moles and our R value. Okay, so we have atmospheres and liters, and of course we've got moles is 0.082057, and that is liter atmosphere over mole K, which leads us to a little bit of a problem with temperature, right? Because this is in Kelvin, but we were given our temperature in Celsius. So we need to do just a little quick side calculation. We need to convert from Celsius to Kelvin. Now, thankfully, that is quite easy. I'm going to change colors. I'm going to put it over here so we're not quite so confused. So all we're going to do is we're going to take our 15 degrees Celsius and we're going to add 273.15. And this will give us our Kelvin. That is 288.15 Kelvin. Now, we do want to keep track of our sig figs here, and we have done addition, so we have to switch rules. It's not just number of sig figs. Remember, with addition subtraction, you're looking at numbers of decimal places. So I started with 1 decimal place in this 15 degrees Celsius, and I used 2 decimal places for my conversion factor. So my final answer, even though I'm going to keep the 0.15, I just need a reminder to myself that I need to round at that first decimal place at the 10th place. But again, just like always, I'm going to put in, sorry, that should not be 2 2s, but 2 8s, 288.15 Kelvin. But again, I'm going to put my little reminder in there that for my significant figures, I'm rounding at that 10th place. So now I've got everything in. Let's double check that units are canceling. So I have liters here and liters here, atmospheres and atmospheres. Okay, so mole is going to be right here. We actually don't want it to cancel because our answer is going to come in moles. And yes, Kelvin cancels as well. So when you're doing ideal gas law, this is the most common value for R, but there are lots of values for R. And you always want to make sure that your value for R is matching up with the units that you are using, because it's really easy to kind of get stuck in one value of R, and always use that no matter what your units are for volume or pressure. Okay. So let me switch back to blue, and let's actually get a number down for our number of moles. And I do have that calculation somewhere. Here it is. It's like, I know I wrote this down somewhere. Again, I'm going to give all of these lovely decimals. This is moles of SO2. Now let's talk about calculating, or not calculating, remembering where our sig figs are. Again, I'm not going to round quite yet because we're not at the end of our problem. I'm just going to remind myself where the sig figs are. So because we're back to just multiplication division, I'm just counting up sig figs. So this first one, I have 3 sig figs. I also have 3 sig figs in my volume. My value of R has 1, 2, 3, 4, 5 sig figs. And I have 1, 2, 3, 4 sig figs in my temperature. Okay, so I am limited by my pressure and my volume. I should have 3 sig figs. Again, I'm not going to round yet. I'm just putting a line under there to remind myself that that is where I need to round as I finish out my calculation. Okay, so one more, well, maybe not one more step, but one more calculation. So this is how many moles of sulfur dioxide I have. I need to convert to grams of sulfur trioxide. So I'm just going to rewrite here my number of moles of sulfur dioxide. And now we're going to put in, finally, our mole ratio. Remember, that's why we got to moles in the first place. We're trying to get to our mole ratio. So I want my moles of sulfur dioxide to cancel, and I am converting to moles of sulfur trioxide. Let's go back to balanced chemical equation. So I've got a 2 in front of my sulfur dioxide, and I also have a 2 in front of my sulfur trioxide. So that is all fantastic. So that is going to cancel, and then it did ask me for grams of sulfur trioxide, so I've got one more conversion. I need to convert out of moles of sulfur trioxide and convert to grams of sulfur trioxide. Okay, so this is molar mass time. That is 1, and I do have that molar mass here. 80.0632. Okay, so my moles of sulfur trioxide have canceled, and now I can do my final calculation. So this, again, with all of the decimals that I know I'm not going to need, 92 times 10 to the 4th grams of sulfur trioxide. Okay, so I need my little reminder mark here for sig figs. So I have 3 sig figs and my moles of sulfur dioxide. This is infinite. And 1, 2, 3, 4, 5, 6. So I'm limited to 3 sig figs in my answer, which means I am rounding right there. So my final answer with the correct number of sig figs is 5 times 10 to the 4th grams of sulfur trioxide. Okay, let's make sure there are no questions after that one. That was kind of a long one. So usually when you're dealing with gases, you're going to have to break it apart into a couple of different steps to get that final result. And again, watch and be careful. If you're converting Celsius to Kelvin, you are doing an addition there. And so you have to make sure that you're using your sig fig rules for addition and subtraction when you're doing your sig figs for that. Okay. We really don't have that much time left. So let me know in the comments, or you can shoot me a message on Facebook. I will show you guys the other stoichiometry problems I have. If you want to see me work these problems for next week, we can do that. If you're still struggling with stoichiometry and maybe you've moved on to limiting reactants, that's kind of another natural place to go after doing what I call simple stoichiometry. But I just want to hear from you. What is going to help you guys the most? So what I've got for this problem here is I've got all constant concentrations. So this is concentration stoichiometry. I also have a problem here where we're going to start with density and volume, and we're going to actually go back to gases as well. So this is another stoichiometry problem with other twists. So I'm bringing in densities and volumes and also doing gases. And then finally, I have another density problem here, and then it goes to concentration. So this isn't with gases, but this is a volume and density, and then going into concentration as well. So these are all problems that are ready to go. And if you would find them helpful and you want to see them work next week, again, just let me know. We are definitely here for you. Thanks so much for joining us at this live stream. I hope you found it helpful. As always, let me know what you guys want. What are you struggling with? What would you like to see? What kind of problems would you like to have worked? And I hope you have a great rest of your Wednesday. Thanks. Bye.